you can't hear the guy that's just on the other side of Kansas City. And hopefully to answer that question and many more is tonight's speaker, and it's K0VXU, Russ Woirhaye. And so, Russ, we'll turn everything over to you, and the floor is yours.
K-Buck W0RR in the net. This is K0VXU, and a very good evening to everyone. And in case you didn't hear it, the name is Warthog here. No, just kidding. Nonetheless, what I would like to do tonight is to speak a little bit about propagation and how you may possibly find out a few things about it. And one of the things I've been taught to do in my years of trying to help people understand things is to have what I call a PPP. That's a purpose, process, and payoff statement. And the purpose of tonight's program is to help everyone understand, at least help, we hope everyone understand, the mechanics of predicting HF and VHF propagation through a knowledge of solar activity. Also, I'd like to point out to you ways of obtaining information on solar activity and tell you of some of the useful tools for predicting the propagation. Process will be a short lecture here by myself, followed by a short Q&A period after the presentation, right here on this repeater. And I think the payoff will be you will have a better understanding of how solar activity affects HF and VHF propagation, how to interpret the SolarTerrestrial Indices that are broadcast by WWV and WWVH, and to gain at least a minimal knowledge of prediction tools available. So first of all, let's move on into a little bit about how solar activity affects radio propagation. The very first thing I would like to speak about in that regard is the ionosphere itself. The ionosphere, of course, is the atmosphere, at least the upper atmosphere that surrounds the Earth, that becomes ionized. And the process of ionization, of course, is through energy release from the sun. There are three distinct layers that can be generally found in the ionosphere at any time of the day. Those are the D layer, as in delta, the E layer, as in echo, and the F layer, as in foxtrot. These layers are at different altitudes. The D layer is the lowest layer, closest to the surface of the Earth. And if you will afford me the opportunity, I will express these in metric units. So the D layer is from 50 to 90 kilometers above the Earth's surface. Now, if you want a quick conversion to the British unit, just multiply it by 6/10. In other words, it's about 30 to 55 miles or so above the Earth's surface. Then the next layer, the E layer, is from 90 to 130 kilometers, and the F layer goes from 130 on upwards, and generally the upper limits of that depends on the latitudes of the Earth of which you reside. The lower latitudes, in other words, closer to the equator, the upper level can be as high as 500 kilometers. Nonetheless, these layers surround the Earth, and these are the layers that are responsible for propagating electromagnetic wave energy, radio frequency wave energy. So what causes this? Well, the solar activity is a direct, or has a direct effect upon the ionosphere. The sun is always outputting energy, and the energy is measured by various parameters. The one that we most normally hear about is the solar flux, and the solar flux is the measurement of energy, and that the units of that are watts per square meter per hertz. Again, that's watts per square meter per hertz, and that's actually 10 to the minus 22nd watts. It's very, very weak, but that's the way they measure it. They measure the solar flux at the 2.8 gigahertz frequency, 10.7 centimeters in wavelength, 2.8 gigahertz in frequency. And the solar flux is a measure of the release of energy, and that energy impinges upon the upper layers of the atmosphere and causes it to ionize. The primary force at work here is the ultraviolet radiation. It takes about 7 minutes to reach the Earth's surface once it leaves the sun. The other release that comes from the sun is what we term the solar wind, and it's generally particles. Protons make up the larger part of that solar wind, and those particles take anywhere from 18 to 24 hours to reach the Earth's surface. These particles mainly affect the geomagnetic field that surrounds the Earth. In other words, the magnetic field going from the North Pole to the South Pole. And a lot of times when these protons and the particles reach the Earth, they strike the upper atmosphere near the poles, release energy, and voila, you have Aurora Borealis or the Northern Lights. Now that we've talked a little bit about the upper atmosphere and how it's ionized, and again, the ionization takes place when energy simply separates molecules into their particles. Essentially, you're looking at oxygen and nitrogen being the two major elements in the atmosphere, and oxygen appears as, I believe, O2, and so you separate it into a bunch of little O's, and those O's form together to form what I call ozone, or part of the ionosphere. Now, the next thing I want to talk about, and I'm probably getting people confused, but let's go on and we'll talk a little bit about how a wave is propagated through the ionosphere, so we can kind of get a handle or an understanding of why 10 meters is open sometimes and other times it isn't. The first thing is that the frequency and the amount of energy and the amount of ionization in the atmosphere determine how much a radio wave will be refracted. And it's not reflected, but refracted. The radio wave is bent through the ionosphere. And depending upon the angle at which it strikes the ionosphere, and again, the frequency and the amount of ionization, you will have a certain angle of bend, or it'll be returned toward the Earth. Sometimes it can be also sent off into space, but generally it's returned toward the Earth. Then, one thing that you need to understand, too, is that when you have refraction, it depends on the altitude at which the wave is returned back toward the Earth. If, for example, the wave strikes the F layer, which is at, say, 200 kilometers above the Earth, it generally will have a skip distance, one hop skip distance of about 2,400 miles, 4,000 kilometers, 2,400 miles. If it strikes the E layer, it more than likely will bounce about 1,200 miles, about half that distance, or 2,000 kilometers. How can you find information about the solar activity? Well, WWV and WWVH, and let it drop. WWV and WWVH broadcast the SolarTerrestrial Indices. WWV broadcasts them at 18 minutes past the hour every hour. WWVH broadcasts them at 45 minutes past the hour every hour. And of course, if you're unfamiliar with the frequencies, I can tell you later on, but I listened just a moment ago and picked up the SolarTerrestrial Indices. And for right now, the solar flux is at 150. That's 150, and that's 150 times 10 to the minus 22nd watts per square meter per hertz, for what that's worth. And there is also another index there. It's called the A index. The A index is a 24-hour average of the amount of disturbance in the geomagnetic field. The K index is a 3-hour average of that same measure of the amount of disturbance. Well, what does this mean? Generally, it means that the higher the solar flux, the better the propagation. But also, you have to understand that the lower the A index and the lower the K index, the better the propagation. Right now, the A index is at 29, which is quite high, and the K index at 0300, or at 9 o'clock tonight, was 5, measured at Boulder, Colorado. The range of the solar flux starts at 63.75 and goes as high as it can go. And the A index is a measure that has got a scale of 0 to 400. That's 0 to 400. Let it drop. The K index ranges from 0 to 9. 0 to 9. And those, as far as I can tell, are unitless, although someone else, probably a little smarter than I, can give you better information on that. Nonetheless, I have seen the K index as high as 8. I've never seen it to 9, but then again, I haven't been studying it more than about 2 or 3 years. And the A index, I've seen it well into the 100s, well into the 100s, 150 or so, 160. That's quite high. And obviously, the higher that number, the more the radio waves are absorbed in the atmosphere, in the ionosphere. So that gives you an idea of what happens when you have solar activity. The solar flux is related to solar flares or sunspots, and there is an equation that relates that. Suffice it to say that the smooth sunspot number is generally somewhat higher than the solar flux number, but they do correlate pretty closely together. And when you listen to WWV, you can hear the solar flux and then convert it to a smooth sunspot number. And why would that be important? Well, let's move on. There are ways of predicting the propagation from any point on Earth to any other point on Earth. In other words, you can sit down and actually calculate what the signal levels are when a signal is transmitted from one point on the Earth to another, and you can actually determine the received signal levels. And a lot of these programs or the calculations use the smooth sunspot number, but then because it is related to the solar flux, some will also accept solar flux for an input. What I would like to do now is to tell you of some of these tools that are out there. Some are in books, some are in magazines, some are provided by organizations, and then there are software programs. First of all, the books. The ARRL Radio Amateur's Handbook is a good source of information about propagation and how it operates and the things that I've spoken about tonight. Another good book is Shortwave Propagation Handbook by George Jacobs, W3ASK, who used to do the forecasts, I believe, in QST. And magazines such as QST, CQ, and 73 certainly are good sources of propagation. I think if you look in there, you'll find that there are propagation charts in each of those magazines. Organizations such as the ARRL broadcast the propagation bulletins, and if you're interested, I have a few here tonight with me I can talk about later on. There is a SolarTerrestrial Forecast and Review that's published by the SolarTerrestrial Dispatch up in Canada, and the software that's available primarily is a Mini-Muff, is what I've seen, and the other one is Mini-Prop. And maybe I ought to speak just a moment about the word MUF, M-U-F. You've all have heard of this. The MUF stands for the maximum usable frequency, and simply that means the frequency at which the radio wave is returned back to the Earth, the maximum frequency at which this will happen. As the frequency increases, the penetration through the ionosphere is greater, and therefore the wave tends to leave the Earth without being refracted back. So the maximum usable frequency is that frequency at which the radio wave is returned to the Earth. There is another thing that you probably have heard. It's called the HPF, the highest probable frequency. The highest probable frequency is the frequency that allows the radio wave to be returned to the Earth at least 10% of the time, and that frequency is generally higher than the MUF. There is another one called the FOT, the frequency of optimum traffic. And this is a frequency at which 90% of the time, wave is returned back to the Earth, and it is generally lower than the MUF. The FOT is the frequency most people look toward for reliable propagation.